Hi, in this video, we'll be continuing our study of statistics by continuing in the introductory of using probability for our statistics course later on. So we have already went through discrete random variables, we have talked about continuous random variables, we talked about their distributions, we talked about how they interact using joint distributions. Another form of interaction is known as the conditional distributions. And it's derived from a name like conditional probability that you have learned, or you can check out my probability series to learn more about it. For discrete case, the conditional distribution is basically when capital X equals to xi given y equals to yi. So in that case, it is defined to be the joint distribution over the marginal distribution at yj. So that is how we denote this conditional probability by. And so we just take an example, which is the given example here. We see that the conditional probability of for x given y equals to 1 is 2 over 3 and 1 over 3. So how is like you already know y is 1, so you just see this. So what's the probability x is 0 given that y is 1? Y is 1 is the total probability of 3 over 8. So it's 2 over 8 over 3 over 8. And for 1 is 1 over 8 over 3 over 8, which is 1/3. And by that way of saying it, we can define the conditional function as the joint distribution equal to the conditional function multiplied by the marginal distribution. And so we can get one side of the equation, just sum this with to x, so it's just summing what all the y's, sum all the y's, and you get the answer. As for the continuous case, like it's always been, instead of doing sum, we just use a continuous function or integral. So for the conditional density, it's just the joint density over the marginal density. So it's nothing too difficult. One thing to remember is that if x and y are independent, then the conditional equals to the marginal distributions. And so the marginal distribution and conditional can be related by the following sense. The joint distribution equals to the conditional times the marginal. Now we want to find just the marginal of y. We just integrate with respect to x from minus infinity to infinity. And we can use these properties to prove that if we can use this idea to now define that for independence, it is just meaning that the joint equals to fx times fy, because over here, if they are independent, we already say that the conditional equals to fy, so this becomes fy, so that's why it's fx times fy. Or these are all equivalent definitions of independence. And this independence would then imply that exy equals to ex times ey, which then you can then say that the covariance actually equals to 0. However, it is possible that the covariance equals to 0, but they are not independent. So you just can look into the textbook to recognize when does this happen. They provide a case in the example. Talking about conditional, it is still a probability, so we can do the same. It's still a distribution, so we can do the same ideas and properties that we want. And that is, there's this thing known as the expectation, but now it's conditional expectation. And it's simply just conditioning on x equals to little x. So what is ey first? Ey equals to the sum of little y times the probability of y. Alright, so if you condition on x, the only thing that conditions here is the probability condition. So now instead of using the distribution of y alone, you use the conditional distribution of y given x, where x is this little x. And for the continuous, you just integrate it. And you can replace this y with any function of y and the formula still holds the same. So one thing you can look is this example where we are given a Poisson distribution and n is the number of points inside the given interval. So we let x be the number of points from 0 to p and find the conditional distribution and conditional expectation of when n equals to little n. So we just need to first find the joint. So the idea is joint and marginal are easy to find. Conditional, you just take the division of each, then you can find it. So you first find the joint, and this is how it will look like. So the Poisson here and the Poisson here multiply together. And to find the marginal, you just take then the marginal of n, which you know the number of points, is already Poisson. So the conditional is just this, and with some algebra you get the following result, which is the binomial. And so if you recognize this to be the binomial, the expectation would then be NP. And so understanding the conditional expectation now, we see that it is given a little x, and so it is some fixed number. And what's now is that we can actually write capital X instead. So instead of writing little x, we change this to just a capital X. So you condition over this giant X, meaning in the end this x can vary, and so you in the end result in a function instead of a sole number. So what do I mean? So for instance, in example A, we found that the expectation of when x given n equals to little n is NP, which is some fixed number. And so if n is now changed to capital N only, so you can vary n, then we write it in this form. The little n just changes to the big N. And so it's a random variable now in the function of capital N. And so because it's a random variable, you can now find its expectation. And its expectation of this must be using, because it's a function of x, it uses the distribution of x to find. And what's more is we can actually say that this expectation actually equals to EY, and the proof is as follows. So we just write EY equals to the sum of this given this. This is the law of total probability. So we just condition over x equals to little x first. But we already know the expectation of y given x equals to little x is this following thing. Okay, so now we sub in this into here, into up here. Okay, so now you got the y, but the y is not in terms of x, so you can pull out to get outside. So you're left with this chunk. But what is this chunk? This chunk is the probability of y, and the probability of y times y, sum over y, is just the expectation of y. And so this theorem is known as the law of total expectations. I hope that's clear. You can re-watch this part to understand first before moving on. And the next theorem is when we have a variable y and we can actually say the variance of it equals to the variance of the expectation of the conditional plus the expectation of the variance conditional. So what is the variance of a condition? Well, it's just this. So it's like quite simply you just take the definition but condition everything on x equals to little x. And so we can define variance of y given x as the following here. And we already know that the expectation of this variance has to be this following. So you can linearize it. So then we can break them down into two parts. So then the variance of this part now is what we need to find. So we can use, so the variance of this is this formula. Remember, it's e bracket whatever squared minus ex whole thing squared. So it's just this. But we know what is this. This is expectation of y. So then we see that variance of y is this, and this part we can also rewrite it in terms of this and the expectation, the law of total expectation form. And if we actually put everything together, we actually obtain to our desired result. Because we add these two together, we see that it looks like this. So they are equal. So next we look at an example, and this is really talking about random sums of a given random variable. So it's like you take you do an experiment n times. So you got x1, x2 all the way to xn, and you take the sum of it. And in this case, how many sums you take is n, and n is a random variable as well, so it's a random sum. Then so in that case, then we say that because the expectation, now we want to find the expectation of t, and the expectation of t, you can use the law of total expectation to get this expectation of the expectation on t given n. And so we just need to find this part inside. So what's the expectation of t given n equals to n? That's just little n times expectation of e x, because now you're given that n is fixed n, so you got n times the sum of the n times of ex as the sum. So then you given the capital N now, so this change to capital, this also change to capital, so this got capital. Then the expectation on t is just this ex. But ex is what? Ex is constant. So you can pull it out and you get this en times ex. And this gives us the intuitive idea that, let's say, what's the total time you take to complete n jobs, and n is random. Then it'd be the average time multiplied by the average number of jobs. Another example is to look at is the variance one, and it's just using the same the formula that we already have. So it's the variance of t equals to this. And then what's this? Well, we already know that it will be ex squared times variance n. And since this thing is n times variance x, then the variance of t capital N is just capital N times variance x. The expectation of it will be en times variance x. And when you sub everything in, you get this formula. And so if n is fixed, then this part is 0. So this is just n, little n times variance x, which is what you already know. And so we'll finally start off with a bit more on what we actually like to study in statistics, and it is known as prediction. And in prediction, it is to so when you predict a value of one random variable, we need to measure the value of this random variable using some instrument and stuff. So you're like So the actual pressure to be measured is unknown and variable, and we can actually model it model them as values of a random variable. So in that case, another example is like the volume of trees is sometimes estimated from its diameter. So you are using another random variable to predict what the random variable that you want has what value. So it is the attempt to predict y from x. And so in the trivial situation, we predict y by a constant value c first, like just not even a function of anything. So it's just a constant value, so y is like fixed. And if we want to choose the best value of c, then what does that mean? It means that the distance between the y's minus the c squared positive distance is like your variance. Expectation of it, the average, is known as the mean squared error. It's like you measure the effectiveness of this prediction, and this average squared error of the prediction, the averaging done with respect to the distribution of y. And so the question now is, what value of c will minimize this mean square error? Because your idea is you want your prediction to be the best, so you want a very effective, so you want this error to be very small. So we actually need, what we need to do is we need to rewrite this into a term that we can really solve, and it is actually equals to the variance of y minus c plus this thing. Okay, so with that, variance of y minus c, since c is constant, equals to the variance of y, and this chunk is basically, you can expand, you can use linearity, so it's ey minus c squared. So that means this part is always positive. So to minimize this part cannot change already. You can only change this, and the smallest value of this is when c is actually the mu. So the optimal choice of predicting y is just taking mu. Now let us consider predicting y by some function hx in order to minimize, or so instead of using some constant, now we use some function hx, and we want to minimize our mean square error by this hx. And as such, we again expand out, and we actually see that it resembles this following form in the end. Okay, so it basically is now you have the condition of x, because it's no longer a constant, so you're like in some function of x. So your mean squared error will actually equals to this variance of y given x, so it's like this, plus the expectation of y given x minus hx. And what does this mean? It means that hx must equal to the expectation of y given x. So you can see how it forms into the place, and it's actually using this formula. You just need to replace appropriately. But of course, this is just one way of predicting and measuring the effectiveness of a prediction using the mean squared error. And if your measure of success is not by the mean square error, then this predictor may not be the best. The best predictor may not be a conditional expectation. Basically, this hx may not be this. So I hope you have understood a glimpse into how prediction works and what is mean square error. It's just like how your actual value differ from your prediction, so it's like your variance in a sense. So you just use this mean square error, and how you're going to find it is this. So if it's a function of x, then you definitely be expectation of y given x, and if it's constant, then it is mu. So that's all for this video. I hope you have enjoyed it. Please feel free to like, share and subscribe, and I'll catch you in the next video. Bye.